In this video we look at section 15.3, which the only new feature in section 15.3 is really the interpretation of a double integral. Okay, some of this we've addressed in other videos, but I wanted to do a little bit more about interpretation in this section. All right, so you know that at this point there is sketching the region of integration. We know that that sketching of the region leads to the setup of the double integral. Okay, and the main thing that you're thinking about there in the setup phase is, do you want to do a dy dx problem versus a dx dy problem? And then there is the evaluation step of the integral. And this may require u substitution. It may involve integration by parts. Any of those integration techniques that you learned about in Calculus 1 and Calculus 2. So I will not revisit those evaluation steps here. What is needed in this Calculus 3 class is interpretation. Okay, we're going to see in a little bit the number of integrals start to multiply. No pun intended. We're going to have lots of different kinds of integrals, and the double integral of a function f, a function of two variables, dy dx over a region xy. This is one of the types of integrals, so we need to talk about interpretation at this point. Okay, going back to the Riemann sum roots of the double integral, when you compute a limit as the number of rectangles goes to infinity, there's a double sum involved here, and we won't fill in any more of the details here. But what became necessary in important in the double integral is that you had the dx dy in the base, and when you multiply dx dy, that you get the area of the base. Okay, and then it was when you brought in the function itself, this function became the height of those rectangles, or these cubes, so to speak. Okay, and so it was the function that gave you the height. Okay, so this leads us to an interpretation that what if the function was equal to 1? If instead of integrating a function, right, a surface that actually has some height where the rectangles actually, maybe lower in one part, lower in over one rectangle, and then maybe over here at the back the rectangles are much taller, right? So what if we make it so that the function has always the same height, 1? How could one interpret the double integral of 1 dA integrating over a region R? Okay, and the key here is that when you do this double integral, you would get 1 dy dx integrating over a region xy. And the key is to just focus on the areas of these the bases, right? If the function height is always equal to 1, then the volume is just the same. The volume of each cube is the same as the area of the base. And from here we can interpret that a double integral of 1 over a region R is a nice way to compute the area of that region R. Okay? So for example, a typically phrased problem would be to find the area of a region. Okay? And this region has a description in terms of a parabola and a line. And they just want you to find the area And that means that you're going to integrate the function f is equal to 1. Okay, and then it's up to you to decide, do you want to do that as a dy dx problem or a dx dy problem? My preference would be to set this problem up as a dy dx problem because we see that from top to bottom, the bottom function is always the parabola x squared, and the top function is always the line x plus 2. No matter what value of x you pick between 0 and 2, right? For the values of x between 0 and 2, the parabola is always on the bottom and the line is always on the top. And that is why we wanted to do the integral dy dx. If you had tried to do the problem as a dx dy problem, we would have had to go from the left to the right, right? And that left and right would have both involved the parabola, right? So how would we have dealt with that? How do you say go from the parabola on the left to the parabola on the right? That sounds a bit confusing. But y is equal to x squared is the same thing as saying that x is equal to plus or minus the square root of y. So there is the parabola on the left, and then there is the parabola on the right. So you would have seen that for certain values of y, between y going from 0 to 1, you can go from the parabola on the left to the parabola on the right. But then after that point, right, so you have this region here shown in red. Then there is another region, region 2, where the line is on the left and the parabola is on the right. And that is why they're setting up two different double integrals here. Okay, and we can see that the double integrals, if you take their limits of integration, the red region here, if you do a region plot on that, x is bigger than the negative square root of y, but x is less than the square root of y is bigger than 0, but y is also less than or equal to 1. So this P1 region, that is the red region shown right here. And then there is a blue region, right? And that blue region is going from x bigger than y minus 2, but less than the square root of y. Y is bigger than 1, but less than 4. So you have two different ways to set up the area integral. Okay. Now, so that's how you get area. All right. The key thing to notice here is that if we're focusing on the units, okay, that when you look at 1 dy dx, dy is measured in like meters, for example. That's this part of the region. Then there is the dx. It is also measured in units, perhaps meters, and that would be this side. And then when you multiply the two together, you get meters squared as your answer. And 1 is just a number, so we get 1 multiplied by meters squared would give meters squared. So the units of this integral are the units, have the units of area. Okay. There is another interpretation of double integrals, and I'd like to look at it now. Right? And what we're seeing here is a double integral over the region that we just had done in the last problem. We have a parabola on the bottom. We then have a line on the top. So we're going from the parabola on the bottom up to the line on the top, and we're going from x from -1 to 2. So here's where we're going from -1 to, 2 is over here. Okay? So this double integral gives the area of the region. Okay? And what we're seeing here in this picture is I've shown one as blue. So we're seeing that at every different point of this region, it's the same blue color, which means that each blue point is at the same height, okay, or a height of 1. What we're seeing in this other problem is a slight change, that now we're seeing the function f of x, y, equal to x plus y, and that there are only certain parts, right here is 1. Certain blue colors, like this kind of middle blue color right here, that is a function that has height 1. But we can see here that at other points of the region, right here in red, for example, right up here at the tip, at this value of x and this value of y, the function has a height of 6. Okay, so what we're seeing here is a plot called a density plot, which we're kind of viewing points in this particular region. We're associating them, points in that region, to a color which gives a density of that region. So here at this point, we would say that it is less dense. This region is made of a material, maybe it's made of wood, for example, at this point. So you've got this little shape that you're trying to cut out, and maybe this part you're making it out of wood, right? And then this tip region, you've maybe made it out of something that is a bit more dense, right? And so this is a region of higher density. And then you've got like so maybe this is like some sort of metal, for example. Okay, and then you've got a mixture maybe in this region, that maybe this is something like plastic or something. And so here we're in this middle region, we're at densities like in the 3 range or something. Okay. So what we're saying here is that this double integral, right, of a function over a region can be interpreted in terms of density. We know that this double integral can be written as y(x), the function f of xy, dy dx, and we know that this part dy dx, the dA part of the integral, has units meters squared. That's an area unit. It's a unit of area. And then we have the function itself, which is kind of like the color part of the graph, and we're going to associate that with density, which has the units of, say, kilogram per meter squared. So it has an area density. And therefore, when you multiply these units out, we know that the double integral leads to adding up. It's a double adding up. So what we're going to do is look at a region here, and we're going to figure out how much it weighs. We're going to take its density, which is the function f, multiply it by dA, which has units of area, kilogram per meter squared, the density times meters squared. So that would be a kilogram. So we would figure out how much this little region weighs in kilograms, and then we would do a double integral to add up all those different regions in terms of mass, kilograms. And therefore we have our final interpretation of this double integral, which is going to be the mass of the region R, whose density function is equal to the function f of xy. So those are two interpretations of the double integral. One where the density function is equal to 1, and one where the density function is not equal to 1. And in the case where the density function is equal to 1, we can say that this mass integral becomes an area integral. And when the function is not equal to 1, this double integral can be interpreted as the mass of the region R. So ends this video.